Welcome to the Explainer. So, have you ever wondered why your AI sometimes just completely whiffs on complex problems, even when you absolutely know it has the knowledge locked away inside? Well, today, we're exploring a massive game changer from Anthropic's applied AI research team. It's called the thinking lever. If you are a researcher, a student, or really just a power user trying to get the absolute most out of large language models, this is the masterclass you've been waiting for. We're going to learn exactly how to unlock the true potential of these tools.
Okay, let's dive into this. Here is our roadmap for the Explainer today. 1. The rise of reasoning models. 2. Unpacking test-time compute. 3. The effort-performance trade-off. And 4. Best practices for researchers.
Starting off with Section 1, the rise of reasoning models and shifting the AI paradigm.
Now, we are rapidly moving away from an era where we expected instantaneous text prediction. The new paradigm is completely built around models that actually need time to think. And Anthropic's internal testing reveals something wild. For complex tasks, especially on agentic coding benchmarks, models perform up to nearly 80% better when they are simply given the tokens and the time to reason through a problem before answering.
Think about it like this, just to ground it in a human analogy. If I ask you, hey, what's 10 plus 10? You don't need a scratch pad, right? You have instant recall. Boom, the answer's 20. But if I hand you a PhD-level physics problem set, you wouldn't just blurt out the first thing that comes to mind. You'd sit down, grab a pen, and really contemplate it. We literally shouldn't expect an AI to instantly solve a massively complex task without giving it a scratch pad to work things out first.
And the scale of this autonomous reasoning right now is just staggering. Newer reasoning models like Anthropic's Mythos can autonomously execute up to 16 hours of human work to a 50% level of accuracy. I mean, really think about that for a second. You give it a prompt, you walk away, and the AI actively thinks and works for the equivalent of 2 full human workdays. It's wild.
All right, moving into Section 2, unpacking test-time compute under the hood.
To truly master these models, we kind of need a shared vocabulary here. So, test-time compute, which is also known as inference-time compute, is basically the act of a model spending tokens during runtime to calculate its next steps. For years, we scaled AI intelligence just by throwing more compute at the training phase. But test-time compute scales intelligence at inference time. It happens right when you hit enter.
Now, when you give a model this compute budget, what's it actually doing? Well, it funds 3 core capabilities. First is the thinking space. This is that hidden scratch pad where Claude considers your prompt and makes a plan. Second is tool calling, which is how it interacts with the outside world, like searching the web or checking your file system. And finally, text output. That's just formulating the actual response that you read on the screen.
And this actually brings us to the evolution of the reasoning process itself. Initially, we had what was called interleaved thinking, which was a super rigid cycle. It was do, then think, then do. But now, we've evolved to adaptive thinking. This gives the model fluid control over exactly when and why it needs to think. It's so much more human. Like, if you're hitting a tennis ball, you react on instinct without overthinking. But if you're writing a deep research paper, you pause to think constantly. Adaptive thinking lets the AI choose its own flow.
Let's look at Section 3, the effort-performance trade-off and the economics of inference. Now, speaking as an AI practitioner, when you are managing the true economics of inference, you absolutely must balance latency, token costs, and intelligence. Consider Anthropic's traffic light simulation prompt using Claude Opus. At a low-effort setting, consuming about 4,600 tokens, the output is functionally pretty simplistic. If you double that token budget to high effort, it yields distinct vehicle types and heuristic driver reactions. Pushing it all the way to max effort incurs a 10x multiplier on both tokens and latency, but it computes a rigorous, physics-bound simulation with highly advanced vehicle dynamics and even visual skyscapes. However, indiscriminately maximizing your compute is a total amateur trap. You have to account for diminishing marginal returns. Scaling from low to extra high effort yields a massive performance delta, but stepping from extra high up to max effort, that frequently consumes a completely disproportionate amount of tokens for a negligible capability bump. Max effort is rarely a Pareto-efficient allocation of your compute budget.
But honestly, low effort isn't just about saving money. It can actually force some brilliant creative problem solving. Anthropic ran this incredible evaluation where Claude played the classic video game Pokemon Red. When they force the model to operate on low effort, the token constraints push the AI into these unique attractor states. To save compute, Claude actively avoided battles, it bought repels, and it used escape ropes to get out of caves just to beat the game faster. It effectively scapegoated the game's mechanics simply because it didn't have the compute budget to think through complex battles. How cool is that?
So, knowing all this, you might be asking, should I use a small model at maximum effort or a huge model at low effort? Let's clear this up. If your academic task requires genuine, deep intelligence, a large model like Opus on low effort fundamentally outperforms a smaller model like Haiku on max effort. You really only want to use the smaller models for latency-sensitive, low-intelligence tasks like simple data extraction.
Which brings us to Section 4, Best Practices for Researchers and Optimizing Your AI Workflows.
It is time to turn all these concepts into a highly actionable playbook for your own academic workflows. Here are your golden rules. Step 1. Build a rigorous test set, also known as evals. Give the AI your hardest problems to find your own ideal balance of intelligence and latency. Step 2. Match the model size to the inherent intelligence required by your task. And Step 3. Provide strict time constraints and budgets.
Now, if you are busy and you just don't have time to run complex evaluations, here is your cheat code. Recommend setting your default effort to extra high. Anthropic research has essentially settled on this as the absolute best starting point for complex tasks. It's the most Pareto-efficient balance of intelligence, speed, and token cost. It hits the sweet spot.
So the crucial point here is how we fundamentally view these models. Listen to this quote from Anthropic. They noted, "When we work with our teammates, I don't tell you don't use your inner monologue," right? Toggling off an AI's thinking process doesn't just save time, it literally removes a core capability. You absolutely must treat the AI like a collaborative teammate. Give it the problem, explain the constraints, and let it use its scratchpad.
The final best practice is mastering budgets. Instead of micromanaging exactly how the model thinks, just set an explicit token budget or a task time limit. You can literally prompt the AI and say, "Hey, take a week to do this." Empower the model to autonomously allocate its own compute so it can actually recognize which tasks are important for your long-horizon analytical work. Let it do the heavy lifting.
We have covered some incredible ground today in this explainer, from the evolution of adaptive thinking to the raw economics of inference and the surprising power of attractor states. By treating test time compute as a deliberate lever rather than just some magic button, you take full intentional control of your research capabilities. So, I'll leave you with this. What massive breakthrough will you achieve when you finally give your AI the time to truly think?